Hello, ladies and gentlemen. Good day. My name is Dr. Augustine Nwajana. Basically, I work at the University of Greenwich, as you can see on my screen. Today, I'll be presenting a research that was conducted by myself and two other colleagues from two other universities. I have Dr. Eugene Obodo from the Aston University. I also have Dr. Emma Swen, who also is a researcher at the University of East London. Now, today I will be presenting our research on formulation for energy distribution in T-junctions for diplexer design. In today's presentation, I'll be going through the following points. We're going to start by looking at the introductory part of the research. We look at the circuit model, the microstrip layout, look at the results, and of course, conclude the presentation. And at the end, there will be a chance for you to ask any questions that you may have. Or, of course, you can also send your questions through our emails that were presented at the end of the presentation. Now, looking at the introduction, the first thing we would like to look at is Diplexers. What is it all about? It's basically a device that is simplest form of a multiplexer that can transmit and receive using the same channel. So we're going to look at how that can be designed. It's not a new technology, but our main originality in this work is how the T junction is being designed. So we have a new formula to enable you achieve a diplexer without going through numerous tuning and optimization. We'll be exploiting quarter wavelength microstrip line in this investigation, and the microstrip line we'll be looking at. We'll be using 1 gigahertz frequency to implement the microstrip line. So that's basically what we'll be looking at today. I'm going to start with the next slide, which is the circuit model. How did we design this? Now, conventionally, diplexers are designed by having a matching network and, of course, a transmit filter and a receive filter. So that means if you have a single antenna connected to one port, you can transmit and receive using the same channel. Now, so our research today is basically based on this matching network. So different designers have used different technologies. Some have used the Y junction in place of the matching network. Some have used the circulator, and of course, it can also be a manifold. But today we'll be looking at a T junction, and then basically how did we design it? We generated a new formulation that will enable you achieve your energy distribution without going through numerous tuning. This is our circuit model. If you look closely, we see that we've designed a three-pole filter, T1, T2, T3, for the transmit side, and we also have three-pole filter for the receive side. And then here we'll have a T junction, which is basically the focus of this investigation. The TL1 and the TL2, we'll be looking at how we can calculate that bit to achieve the actual microstrip diplexer. Now, these are the parameters that we considered in our research. We started with two filters. The first filter has a center frequency of 2.6 gigahertz, and the second filter, which is the receive filter, has 3 gigahertz as its center frequency. Both TX and RX have the same fractional bandwidth of 3%. The return loss for both filters will be looked at 20 dB. And then for the electrical length of TL1 here, we selected 63 degrees, and of course TL2 at 67 degrees. And as I mentioned previously in my last slide, both TL1 and TL2 will be considered at a 1 gigahertz. Now, let's look at the microstrip layout. If you look closely, you'll see that we have actually designed this T junction. Here we have the two filters. So filter design is not something new. So there's a lot of references on how to design filters. So it's not new. We just designed a filter using some of the conventional methods that are well published in research papers. But our main work is on the T junction. So how do we calculate to get 47.8 as the length of this transmission line, microstrip line, and of course 49 as the length of this microstrip line. Just to be clear, there's no tuning done in this work. This work was not tuned. It was just basically by formulation, which we're going to present in a minute. Okay, so here we have the materials that we use for our simulation. Here we use substrates used for this design is the RT Duroy 6010 LM. The substrate dielectric constant was 10.7. We use a loss tangent of 0.0023, which is recommended by the manufacturer. Of course, the thickness of the substrate material is 1.27 millimeters. Now, the formulation that we propose here is here where we have that TL to calculate the TL1, the TL2 value. What we did was to this is the formulation we have, the electrical length plus 90 degrees divided by 360 multiplied by the guided wavelength at 1 gigahertz. Yeah, now this 90 degrees here is basically saying it's basically showing us the amount of offset. So that's what we looked at in the lab, and we try different design, and we can see that it works. Now, so if we plug in the value, the electrical length, which is basically 63 for TL1, 67 for TL2, as shown in my previous slide. If we plug that into this equation, we get our TL1 to be 47.8 and the TL2 to be 49 millimeters. So that's basically how we did this. Without any further tuning, we achieved our results with this. Now, moving on to the results, we can see here that we have a well matched filter. You can see here the return loss is at 20 decibels as we expect. And then of course we can see also the insertion loss is basically 1.1. That's what we measured. 1.1 is measured insertion loss that we achieved for both the circuit model and of course the microstrip layout. So here we have the isolation between the two channels. So you can see the isolation measured here for the circuit model. We have an isolation of 50 decibel, but for the microstrip we got something roughly about 42 dB as that, which is very good. Now we now have these are basically the results we achieved. As I said earlier on, the transmit and receive insertion losses were achieved at 1.1 decibel. The return loss is 20 dB, which is expected. The circuit model isolation is 50 dB, and while the maximum layout is 42 dB. The TS and the ROS selectivity is high, as you can see. And of course, for the Chebyshev filter, because what we did here is a Chebyshev filter, we expect a roll-off, a medium roll-off, so which is exactly what we achieved in this investigation. In conclusion, we have been able to present a formulation that will help achieve a diplexer without going through tuning and optimization. The prototype diplexer that we presented shows good results. So we did not use any tuning nor optimization, just formulation to achieve these results. This simulation was done using the ADS circuit for the circuit, and of course ADS momentum for the microstrip layout. We presented our results and of course made comparison, and of course it shows that this work is valid. Now, if you have any questions, this is the time to ask your question. Alternatively, you can email your questions to this, the email you can see on your screen. I will definitely give a reply. We're also happy to receive comments on the work done by this email. Thank you for listening. I hope you enjoy the rest of your day. From me and my colleagues, bye.